The following content is supported by victoris.org.
Hi everyone, today I'll be talking about dynamic programming and how to use this technique to solve various algorithmic problems. So here's the agenda. We'll go through these following examples to illustrate the concept of dynamic programming. So dynamic programming, roughly speaking, is splitting big problems into smaller subproblems. This definition isn't very illuminating, but don't worry, as we go along through the examples, it'll become clearer. It is also about memorizing answers to the smaller subproblems so we don't recalculate the same values over and over again. In other words, dynamic programming is brute force plus memorization. So let's go through a simple example of Fibonacci. So we know that the Fibonacci sequence is defined as follows. The base cases are that the 0th Fibonacci number and the first Fibonacci number are 1, and for the second and beyond Fibonacci number is defined by this recursive relation. So if we call f of 6, it depends on f of 5 and f of 4, right? And f of 5 is going to itself depend on f of 4 and f of 3. So if we want to code this into a function, we can do so recursively. So this is a function that returns long, and it takes in a parameter n and returns the nth Fibonacci number. So the base cases are as follows. These two conditionals cover the n equals to 0 and n equals 1 case. If n is 2 or greater, the Fibonacci number, the Fibonacci function, would call itself with a smaller parameter. So what's the time complexity of this? It can be shown that it is at least 2 to the n over 2. Why is that so? The answer is because f of 6 calls f of 4 twice plus this slight overhead of f of 3. So f of 6 calls f of 5 and f of 4, and f of 5 calls f of 4 and f of 3. So you can see that f of 6, whenever we call f of 6, right, f of 4 gets called twice, and there's this additional overhead of f of 3. So with that, we can conclude that the time cost to calculate f of 6 is at least twice the time cost to call f of 4. So f of n, if we generalize this, f of n would call f of n minus 2 twice, and this would lead to this exponential time complexity. Is there a way to speed this up? One observation you can make is that there's multiple values being calculated again and again. For example, we call a function f of 0 many times, right? And f of 1, we call it many times as well. Same goes for f of 2 and f of 3. When in fact, these functions, wherever parameter it takes in, if that value is calculated already, there's no need to calculate the value again. In this case, if we call f of 4 and we calculate that the f of 4 is equals to 5, then we do not need to recalculate f of 4 again and incur all that time. So the first approach to dynamic programming is known as top-down memorization, which is basically the same recursive function, just that we add 3 lines. The first line is declaring an array that will store the answers to the function calls. This array will be initialized to an array full of zeros. In this case, if memo of I is 0, that means we have not calculated fibo of I. So in the function call, we check if memo of n is not 0, then that means we have calculated the value of fibo n, and so we return memo of n. Now if we have not calculated fibo of n, then memo of n will be 0. And in this case, we want to calculate fibo of n by calling fibo of n minus 1 plus fibo of n minus 2. Now after that, before returning it, we want to store it in the array memo of n, and then we return it. This way, if we call fibo of n again with the same value of n, memo of n will no longer be 0, and that will indicate that it has been calculated before. And so instead of calling fibo of n minus 1 plus fibo of n minus 2, we just return memo of n directly. In this way, we avoid recalculating the fibo of n for the same n many times. And the time complexity for this is O of n, because for each value of n, fibo of n will only be calculated once before it is memorized and returned immediately. Another approach to this is bottom-up. We declare an array to store the Fibonacci values, and we set the base cases before calculating the rest. After that, we just have a for loop that goes through the entire array, and fibo of I will be calculated based on fibo of I minus 1 and fibo of I minus 2. I believe this is the more intuitive approach. However, the bottom-up approach depends on an ordering on the DP states. In other words, we need to find an ordered sequence of fibo of I to calculate. If we try to calculate fibo of 4 before calculating fibo of 3, then this line would not make sense, because fibo of 4 depends on fibo of 3 and fibo of 2. If we interpret the DP states as a directed acyclic graph, this is a statement that we must find a topological order on the deck. But if that didn't make sense to you, it's alright. Now one might be quick to conclude that the bottom-up approach is always easier to implement than the top-down approach. And that's because in the case of Fibonacci, this is indeed the case. However, in other dynamic programming questions, sometimes the states don't have an obvious topological order, and the order in which we need to calculate the states can be non-trivial. Such is the case for DP on graphs or trees. Now, can we beat O of n for Fibonacci? The answer is yes, and we'll talk about that next time in math session. And now you can attempt the following question. Next, we'll talk about static sum.